Welcome AP Statistics. This is chapter 22. We're going to be talking about inference, but about the mean rather than a proportion or difference of proportions. So this is new content about inference. We need to start by revisiting the most important theorem debatably in all of statistics, which is the central limit theorem. The central limit theorem says when random samples are drawn from any population with mean mu and standard deviation sigma, the means of those samples, shall we say x bar, have a sampling distribution with the mean the same as that of the population and a standard deviation the same as the population except divided by the square root of the sample size. So the greater the sample, the less the variation. This is true regardless of the distribution of the population, so long as n is sufficiently large, which means for all but the most skewed populations, a sample size of 30 will suffice. So let's employ this old knowledge that we've had. Based on weighing thousands of animals, the American Angus Association, the AAA that you haven't heard of, reports that mature Angus cows have a mean weight of 1,309 pounds with a standard deviation of 157 pounds. This result was based on a very large sample of animals from many herds over a period of 15 years. So let's assume that these summaries are the population parameters and the distribution of the weights was unimodal and reasonably symmetric, as reasonable as we can expect for real-world data. What does the central limit theorem, or CLT, predict about the mean weight seen in random samples of 100 mature Angus cows? Well, here's what we can expect. It's given that the weights of all mature Angus cows, says our textbook, have mean of 1,309, standard deviation of 157. Both are in pounds. Because n equals 100 animals is a fairly large sample, I can apply the CLT. I expect the resulting sample means for, let's use variable y bar, will average 1,309 pounds, notice the same number as the population, and have a standard deviation of, here it is, standard deviation of my sampling distribution of sample means is the same as that of the population, except we divide by the square root of n, which means we're dividing by the square root of 100, which is 10. Move that decimal, 15.7 pounds. All right, so a little less than 16 pounds. If we were to describe this distribution a little more, it would behoove us to use a normal model. The model would be centered at 1,309 pounds, then about 16 pounds below, and then 16 pounds above. We would have about 68% of the means of these samples of 100. So 68% of these large samples would be in this first interval. Then 95% of means of large samples would be in an interval about 31 to 32 away from 1,309. And then 3 standard deviations out, so 3 of those 15.7 pound intervals out, we would have almost all means of large samples. So that gives you an idea about how the mean of a sample of size 100 would be distributed. But this is not the true story of chapter 22. That is a review of old content because we are going to throw a massive monkey wrench into all this. What about small sample sizes? Well, we have this gentleman named William Seeley Gossett who lived at the end of the 1800s into the early 1900s. He was the chief experimental brewer for Guinness. Yes, that is the brewer out of Ireland. To perform his job, Gossett routinely had to work with sample sizes for which the population standard deviation was unknown. For large samples, the sample standard deviation is not going to be far from the population standard deviation, but for small samples, the sample standard deviation is wildly off, okay? tends to be pretty wildly off. The smaller the sample, the more unpredictable things get. And that's the problem that Gossett dealt with. Now, when I talk about small, we are talking about single-digit samples. This is pretty far from our benchmark of 30. So Gossett was dealing with samples in the single digits, all right? And not the upper single digits, mind you. We're talking about 5 and below here. So Gossett developed a model for such small samples called the t-distribution, right? Now, here's where we get into a bit of math history. Employees of Guinness were forbidden to publish, all right? And that's because when you work for a company and you benefit the company and you contribute to the success of a company, there tend to be company secrets, all right? And we're not supposed to publish the secrets to our success in brewing beer, all right? So Gossett, after much pleading with Guinness, was able to publish his work, but he had to use a pseudonym, all right? So kind of like Mark Twain or Dr. Seuss, he had to take on a pseudonym, and he took on the pseudonym Student with a capital S. To this day, the model that he came up with, this statistical model that is a bell curve, but it's a really fancy, interesting, wild kind of bell curve. It's actually a family of bell curves, is called Student's T, all right? Now, some textbooks have taken to calling it Gossett's T. That's fair enough, but generally this is still called Student's T because that is the original name, and there's a fun story associated with it to boot. Now, let's talk about the difference between Student's T and the normal model Z, okay? Both curves are bell-shaped. For large samples, the curves are nearly identical, okay? However, Student's T changes shape depending on the sample size, or more specifically, technically it changes according to what are called degrees of freedom, hence why Sam the Eagle is in the top right-hand side, talking about the American way. We compute the degrees of freedom by considering the sample size n and the number of parameters we are estimating, okay? So you may hear a stats teacher or a stats prof say it's generally sample size minus 1. That is generally the case, but technically we compute degrees of freedom by taking the sample size and subtracting the number of parameters we're estimating. So since we're only modeling a distribution for the mean of a small sample, all right, that means the degrees of freedom is n minus 1. We have one parameter we are estimating, namely the mean, so we subtract 1 from n, and that would give us our degrees of freedom. We often denote degrees of freedom lowercase d, lowercase f. So the notation for a T model is T with some number of degrees of freedom. So for a sample of size 15 being used to estimate one parameter, we would use T subscript 14. Hopefully it's clear enough. So let's talk about the difference between Student's T and the normal model Z in terms of their appearance. T morphs to account for increased variability for small samples. We say that T is not just one curve like Z, but it is instead a family of curves. You will notice that the normal distribution, which normally peaks at 0.4 and the tails go out to the left and right, is similar in form to these T curves, but you'll notice a key difference. If you look at the red T curve, that would be Student 1, all right? That's a little way of saying this would be the T model T subscript 1, which means in our chapter right here, we'd be working with a sample of size 2, which is theoretically possible. Now, sample sizes of 2 are wildly unpredictable, so we need a curve that accounts for more variability. More variability means more area at the extremities. So you'll notice that in the middle of the curve, we kind of push things down, and kind of like if you were to push down a lump of sand, the sand goes outwards in all directions. So if we were to push down on the normal distribution curve a bit, that excess area would go out to the tails. That means that we are accounting for more variability. There is more probability that our results could be more extreme. okay? Now, as we increase sample size, say t sub 5 and t sub 30, our curve looks more and more like the classic normal model that peaks at 0.4, all right? By the time we get to 30, the curves are almost indistinguishable. So now we can talk about confidence intervals for the mean. Our confidence interval for the mean will be a one sample t interval, and that goes for samples of all sizes. So if you took my other stats class, in general, our rule was for samples of size 30 or greater, you use Z, and for samples of size under 30, you would use T. In this case, in AP Stat, when we are dealing with the mean, we play it safe and we use the T model in all cases, okay? So here are the details for a one sample t interval for the mean. Now, when we talk about assumptions and conditions, that's going to be on a future slide not too long from now. When we talk about those, you'll see that there are some that are the same as before, but others that are different. But after we've established those, we're ready to find the confidence interval for the population mean mu. The confidence interval is centered at the sample mean, all right, centered at our sample mean, plus or minus some t star value, which is like a z star value, all right, and this n minus 1 just means this is the subscript for sample size minus 1, that's the degrees of freedom. So you got a t star rather than a z star times the standard error of the sampling distribution of sample means, where the standard error is the sample standard deviation divided by the square root of the sample size. The critical value, t star, depends on the particular confidence level c, just like a z star value that you specify, and on the number of degrees of freedom, n minus 1, which we get from the sample size. Though you may encounter problems on the AP test where knowledge of this formula is helpful, one, it helps that it looks like all of the other formulas for confidence intervals we used. It has the same form. We will generally be relying on the calculator for calculations involving t. So that takes some of the stress off of it. Knowing the form of the confidence interval is helpful, but for the actual computation, you got your calculator to help you. All right, so here's a problem. In 2004, a team of researchers published a study of contaminants in farmed salmon. Fish from many sources were analyzed for 14 organic contaminants. The study expressed concerns about the level of contaminants found. One of these was the insecticide Mirex, which has been shown to be carcinogenic and is suspected to be toxic to the liver, kidneys, and endocrine system. That is bad news. One farm in particular produced salmon with very high levels of Mirex. After those outliers are removed, summaries for the Mirex concentrations in ppm, parts per million, in the rest of the salmon that are farmed are n equals 50. The mean is 0.0913 parts per million, which seems like a small number, but we'll learn that's actually a rather large number in this case. And standard deviation is about half that, okay? What does a 95% confidence interval say about the Mirex? All right, so first we're going to check to make sure we've met the conditions to construct a confidence interval. That's on the next slide. Then we're going to use a t-interval on the calculator to find a one sample t interval and interpret this interval in the context of the problem. Let's look at those assumptions and conditions. All right, so let's look at these assumptions and conditions to use the t model. Independence can be assumed if the following conditions hold. All right, we need to be able to assume independence. And we can check the randomization condition, and that condition states that data arise from a random sample or a randomized experiment. Same randomization condition as before, no surprises there. And 10% condition, the sample is less than 10% of the population. Any more than that, we cannot assume independence. Ho-hum, moving on. We also need to assume the data are not badly skewed, so we need to check the nearly normal condition. nearly, I could even put some air quotes next to nearly, because you're going to see what we can get away with in this chapter, and it's kind of funny. I may or may not have a meme about it, and you'll see that meme in just a little bit. The data we collect appear, air quotes, to be unimodal and symmetric without clear skewness or outliers. Okay, and we'll see what counts as nearly, and you may be surprised and maybe a little disturbed. The smaller the sample, the more important this condition is. So if we have big samples, we can get away with a lot, and you will see that. But if we have really small samples, we either need to abort mission, or we go through the test and say we're going to take this with a grain of salt. Especially for samples under 30, it is good to plot the histogram of the data to ensure this condition is met. For large samples, so long as there is not severe skewness, we are safe to use T. All right, so those are the three conditions we need to check to ensure for the first two, randomization and 10%. If we can confirm those, we can assume independence. And we need to also make sure that the distribution of our data that we collect are nearly normal, nearly air quotes normal. So we see a histogram about these data involving the salmon and the Myrex parts per million over on the right. And we need to use that if we're going to make sure that all the conditions are met, specifically that last condition, the nearly normal condition. All right, I'll let you decide whether or not that is nearly normal. But randomization condition, the fish were chosen randomly from a diverse set of farms. We can assume the sample is representative of the population of farmed salmon. Not a bad assumption. Right? And 10% condition, 150 is obviously far less than the population of farmed salmon. Fish farming is quite common worldwide. 150 is way less than the population there. The nearly normal condition, the data are unimodal, though not very symmetric. No matter, we have a sample of 150, and that is large enough to compensate for the skewness of the data, so we say, good enough. So now let's find this confidence interval. We're going to go to stat. We're going to go to tests, and we're going to go down to T interval. Hit enter. We are given sample statistics, which is great. We are given that x bar is 0.0913, S sub x, our sample standard deviation, is 0.0495, sample size of 150, and we want ourselves a Ronald Fisher approved 95% confidence interval, and so we hit calculate. And there it is. So we have found our confidence interval is about 0.083 parts per million to 0.099 parts a million, which means we can be 95% confident that the true mean concentration of Myrex is between 0.083 parts per million and 0.099 parts per million. There you have it.